So hello everyone, good evening and all. So today we will continue the chemical bonding and its molecular structure, part 2 of our crash course. So yesterday we have seen the BSEPR theory and some of the hybridization concept, etc. Right? And today we will look into the bond parameters, that is bond length, bond angle, bond enthalpy, and bond order. And then we will look into the very important topic, molecular orbital theory. So we will see the gist of it and then we will solve some problems related to these topics. Okay, so I'll start with bond parameters. So there are 4 bond parameters and the first one is bond length, the second is bond angle, third is bond enthalpy, and the fourth is bond order. Okay, so moving from the first, that is bond length, from the picture that is given here itself, you can understand what is bond length and the other bond parameters, but we will discuss some more in detail about the each topic. Okay, so what is bond length? So it is the equilibrium distance between the nuclei of two bonded atoms in a molecule. So I'm going to take a molecule. It is the first red color atom is atom A and the blue color is atom B. So there are nucleus present at the middle of the center of this each atom, right? So that distance. So this, if you connect the nucleus of both the atom, you will get one thing, and that is nothing but the equilibrium distance. And if I cut this like this, I will get the radius of A separately and the radius of B separately. Now the whole distance is denoted by the letter R, capital R. So capital R is equal to the radius of atom A plus radius of atom B. So that capital R is called as bond length. It is called as bond length. Okay, equilibrium distance between the nuclei of two bonded atoms in a molecule is called as bond length. Now, some bond length values are given here for some molecules. You don't have to memorize all these values. Just observe whether it is increasing or decreasing for a particular series. Okay, for hydrogen, fluorine, chlorine, bromine, iodine, nitrogen, oxygen, and for all the hydrogen halides, it is given. Just observe. So when you observe for hydrogen halide, from HF to HI, the bond length increases. Okay, like this, just observe the thing alone and keep in your mind. Now we will move on to the next bond parameter, that is bond angle. So what is bond angle? The angle between the orbitals containing bonding electron pairs around the central atom in a molecule or a complex ion. Okay, so I'll take H2O molecule as an example for you. And here H2O has 2 OH bond, right? So there are 6 valence electrons for oxygen, 2 is there for bonding and remaining 2 is there for lone pair. Now these two are the bond pair of electrons. Now an angle is created by this bond pair, which is 104.5 degree, and this is called as the bond angle. In case of CH4, if you see for the bond angle, for CH4 the bond angle is 109.5 degree. And for NH3, if I take the bond angle, nitrogen will have 3 bonds and 1 lone pair of electron, right? So H and H bond angle here it is 107. So the bond angle for these 3 species are very, very important. Just have a note of it. So these are the bond angles. It is the angle between the orbitals containing the bonding electron pair around the central atom. Okay. Now moving on to the third bond parameter, bond enthalpy. So we can call this as energy also, bond energy also we can say. The energy required to break 1 mole of bonds between two atoms in gaseous state is called as bond enthalpy. Now I'll take hydrogen molecule. So there is one bond between two hydrogen atoms, right? So if I want to break this bond, I have to supply 435.8 kilojoule per mole of energy to separate this into its constituent atom, gaseous atom. Okay. Now for molecules containing multiple bonds, if a molecule contains 2 bond or 3 bond, that is double bond or triple bond. For double bond, we can take oxygen as an example. There are 2 bonds between oxygen. Now you see the energy required to break the 2 bond is little bit higher than breaking a single bond. Okay, it is 498. Now if I want to break 3 bond, like in case of nitrogen, we have 3 bond, right? If I want to break all these 3 bond, you see maximum amount of energy, 946, just double the amount of this, right? So more amount of energy is required to break the triple bond. Energy required to break the bond is called as bond energy. Now all the 3 molecules which you are seeing on the screen, they are diatomic, homonuclear diatomic species. If we see for the polyatomic molecules, polyatomic means more than 2 atom containing molecules. Now for those molecules, measurement of bond strength is very, very complicated. Okay. Suppose if I take water as an example, water molecule contain 2 OH bond, right? So 2 bonds are there. First I have to break 1 bond, then I have to break the second bond. So I have to break 1 by 1. So I am breaking this first bond. This is first bond, this is second bond I'll take. Now I have to break this one. If I break this first bond, what I will get? I will get 1 hydrogen and then 1 OH, right? So that is formed here. The energy required to break the first bond is 5 not 2 kilojoule per mole. If I want to break the second bond, that is OH, this bond, then I have to supply 427 kilojoule per mole of energy. If I give that energy, it will give the corresponding constituent atom, hydrogen and oxygen. Okay. For this type of species, how to tell the bond enthalpy? If in the exam, they are asking you to find out the bond energy for water molecule, which value you will give? 502 or 427? Both the values are wrong. For polyatomic molecules, we have to find the mean bond enthalpy value. That is average bond enthalpy value we have to find out. How to find out? It is equal to the total bond dissociation enthalpy divided by number of bonds broken. Total bond dissociation enthalpy divided by number of bonds broken. So add both the value and divide by the number of, how many bonds has been broken for water molecule? It is 2, right? So for water molecule, 502 plus 427 divided by 2. So it will give 464.5 kilojoule per mole. So this is the bond energy value for water molecule. So if they are giving for NH3, if they are asking for NH3, so NH3 is 3 bond pairs. So we have to break 3 bonds. So just add all the delta H values, 3 delta H values and divide by 3. So that will give you the average bond enthalpy for ammonia molecule. Okay. So this is how we have to calculate. Now coming to the bond order. So the number of bonds between the 2 atom and a molecule is called as bond order. Very easy. You see here. So hydrogen and hydrogen has only 1 bond between it. So the bond order is 1. And for oxygen it is, for oxygen it is 2. For nitrogen it is 3 and for carbon monoxide also it is 3. The number of bonds is nothing, between the 2 atoms is nothing but the bond order. And for isoelectronic molecules and ions, they have identical bond order. You see here, F2, the atomic number for fluorine is 9 and 9 plus 9 is 18. And O2 2 minus, if you see, atomic number of each oxygen is 8. 2 oxygen are there, 8 plus 8, 16, and it has gained 2 electrons. So 16 plus 2 will be 18. So both the species are having the same number of electrons. So they will have the same bond order. Okay, in case of nitrogen and carbon monoxide, they have same number of electrons. So the bond order for both the molecule is 3. Okay. Now I'll give you a relation between bond length, bond order and bond enthalpy. If bond order is more, bond enthalpy is also more, but bond length is less. So what is the relation? Bond order is directly proportional to bond energy, but these two are inversely proportional to bond length. So this is the relation which you have to study. Okay. So this is about the bond parameters. Now we will move on to the second topic, that is molecular orbital theory. So I'll quickly revise the postulates of molecular orbital theory and then we will solve the questions. So the first postulate says that Electrons in the molecule are present in various molecular orbital as the electrons of atoms are present in the various atomic orbital. So in left hand side and right hand side, you can see some orbital, one is orbital. So that is atomic orbital. The one which is present in the middle, they are called as molecular orbital. So electrons are present in the molecular orbital like it is present in the atomic orbital. That is postulate number 1. Only atomic orbital of comparable energy and proper symmetry combine to form molecular. Not all orbital will combine. Only those are which are of comparable, like 1s and 2s, 2s and 2p. Okay, so 1s and 4s will not combine to form the molecular orbital. 1s and 2s. So the energy difference should be less, and the symmetry should be proper. Then only they will form. If one orbital is like this, and if the other orbital s orbital comes like this, they will not form the molecular orbital. Okay. And coming to the third postulate, an atomic orbital is monocentric when the molecular orbital is polycentric. That is obviously true, right? So this is an atom. Atom has only one nucleus. One atom has only one nucleus. So here one hydrogen atom is having one nucleus. Now if I go for hydrogen molecule, we have two hydrogen atoms. So it will have two nucleus. So it is dicentric. It is influenced by both the nucleus. So it is polycentric, but here it is monocentric. Coming to the fourth postulate, total atomic orbitals combining is equal to the total molecular orbitals formed. If two atomic orbitals are combining, two molecular orbitals will form. Here you see two s orbitals are combining, and here two molecular orbitals are being formed. So molecular orbitals formed are called as bonding molecular orbital and anti-bonding molecular orbital. The one which is going lower in energy than the atomic orbital energy level, they are called as bonding orbital. And the one which is higher in energy than the atomic orbital is called as anti-bonding molecular orbital. Bonding molecular orbital is denoted by the letter sigma, pi, like that. Anti-bonding is denoted by the letter star, sigma star, pi star. Bonding molecular orbitals are having very low energy. Anti-bonding is high energy. Energy and stability is inversely proportional, right? So low energy is more stable. High energy orbitals are less stable. So bonding orbitals are more stable. Anti-bonding orbitals are less stable. So when you add both the orbital, they will give rise to bonding. And when you subtract, it will give the anti-bonding. Got it? Coming to the last postulate, the electronic configuration in various molecular orbitals are governed by the same three rules that we use to fill up the electrons in the atomic orbital. Okay, Aufbau principle, Hund's rule, Pauli's exclusion principle. What is Aufbau's principle? Electrons are arranged in the increasing order of energy level. So in the same way, electrons are arranged in the increasing order of their molecular orbital energy level. And Hund's rule, no pairing occurs until all orbitals are half full. The same thing we have to follow here also. Pauli's exclusion, one orbital can take only two electrons, and those two electrons should be in opposite spin. So that you have to follow for molecular orbital also for filling up the electrons. Okay. Now, these are the 5 postulates. Now, I'll show you the molecular orbital energy level diagram for the species which contains 14 electron and less than 14 electron. Examples are boron, boron molecule, carbon molecule, and nitrogen molecule. For all these 3 species, or for any other heteronuclear atomic species which is having less than 14 electron or equal to 14 electron species, you have to go with this order. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then here pi 2px, pi 2py, and then sigma 2pz. So this orbital is called as sigma 2pz. And above that pi star 2px, pi star 2py, above that sigma star 2pz. Okay. So here 1, here 1. Sigma 2s, sigma star 2s. And here 2 pi orbital and 1 sigma, and here pi star and sigma star. So you have to follow this triangular type of concept. Okay, for the first case. And the electronic configuration you can see sigma 1s, it is going in the increasing order of their energy level. Okay, This electronic configuration general formula you can keep in mind. Now for the system which has more than 14 electron containing system, oxygen, fluorine. Oxygen has 16 electron and fluorine has 18 electron. Okay. For this type of species, what we have to do? Everything remains same. Everything remains same. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, everything remains same. Just you have to interchange this. The sigma 2pz comes here and pi 2px and pi 2py goes above. Okay. So that is the only change. Pi star, sigma star, they remain same. Upper part remains same. Antibonding orbital remains same. But bonding orbitals are just inverted. So this inverted triangle we have to use. Okay. And the electronic configuration we can keep in mind. Sigma 2pz is going lower in energy. Then comes pi 2px and pi 2py. Okay. So this is the molecular orbital energy level diagram that we have to follow for both the cases. Okay. Less than 14 electron and more than 14 electron. Now, what are the applications of molecular orbital theory? Okay. What and all we can find out by using this theory. So we can find 4 property. One is bond order and the other one is bond length. Third is stability. Fourth is magnetic nature. Now, what is bond order? So we have one formula to calculate the bond order using molecular orbital theory. It is equal to Nb minus Na divided by 2. Nb means number of electrons in bonding molecular orbital. Na is the number of electrons in anti-bonding molecular orbital divided by 2. Now every time we cannot draw the MO diagram and then we can count the electrons in bonding, anti-bonding and all, no? So in that case, you can use this trick. Just calculate the number of electrons given in the species. Suppose if I am having oxygen, how many electrons are there for oxygen? For one oxygen, 8 electron. 2 oxygen means 8 plus 8, 16, right? So just find out this number of electrons and use this table. Start from, go from 10 to 18. Start from 14. For 14, the bond order should be 3. And for 13, you subtract 0.5. And for 12, subtract 0.5. So 0.5, 0.5, you subtract above and below also. Okay, keep the 14 as your reference. If the number of electron is equal to 16, then the bond order is 2. So oxygen will have double bond. Okay, if I'm having fluorine, so fluorine atomic number is 9. So 9 plus 9 is 18. So 18 means the number of bond order is 1. So every time you don't have to draw the MO diagram and calculate. You can use this trick table to find out the bond order easily. If I am having any ions like O2, 2 minus ion. So we know O2 has 16 electron and it has gained 2 more electrons. So 16 plus 2 is 18. So O2 2 minus bond order is, for 18 it is 1. So the bond order will be equal to 1. Okay. Clear? So this is how we are going to find out. Then coming to the second application, bond length. So it is inversely proportional to bond order. The compound which is having the highest bond order will have the lowest bond length. You see here among this carbon-carbon, single bond, double bond and triple bond. In triple bond, the bond order is 3. When you compare the bond length, the triple bonded system is having the very least bond length value, 120. They are inversely proportional. And coming to the third property, third application, stability. It is directly proportional to bond order. Stability is directly proportional to bond order. One which is having the highest bond order will be more stable. The one which is having the least bond order will be less stable. The number of electrons in bonding orbital is greater than anti-bonding, it is stable. If it is less than or equal, it is unstable. Here you see, this is the bonding molecular orbital. It has 2 electrons. And for hydrogen in anti-bonding, 0 electron. So here Nb is greater than Na. So hydrogen molecule is stable with 1 bond order. And for helium molecule, you see helium, number of electrons in bonding is 2 and in anti-bonding also 2. So Nb minus Na, Nb is equal to Na. Nb is equal to Na. If it is equal, then the molecule is unstable, right? So helium molecule does not exist. Helium molecule does not exist. So this is how we are finding out the stability of a species. Got it? Now coming to the fourth application, that is magnetic nature. So there are two different types of magnetic property. One is paramagnetic and the other one is diamagnetic. If a species has unpaired electron in it, it will be attracted towards the magnetic field, and we call those substances as paramagnetic substances. If all the electrons are paired up, then it will be repelled by the magnetic field, and we call them as diamagnetic substances. We can tell by looking into the MO diagram itself, okay, whether it is paramagnetic or diamagnetic. So they are so easy. Now, using this concept, using MOT and bond parameters, we will try to solve the previous year's questions of JN NEET. Okay. So moving on to the first question, 4 statements are given to us. We have to find out the correct statement from the options given below. So let's start from the first. NF3 molecule has a trigonal planar structure. So what is the structure of NF3? It is NF3 with one lone pair. So it is trigonal, pyramidal in structure. It is not planar. It is pyramidal. So the first statement is incorrect. Bond length of N2 is shorter. N triple bond N, but O double bond O. So bond order and bond length are inversely proportional, right? The one which is having the highest bond order will have the least bond length. Means nitrogen will have the least bond length. So that is correct. Isoelectronic molecules or ions have identical bond order. Yeah, that is also correct. Just now we have seen. Okay, under the bond parameter. And dipole moment of H2S is higher than that of water molecule. This is H2S. And this is H2O. Oxygen is more electronegative than sulfur. So if an atom is more electronegative, obviously that atom containing electronegative atom containing molecule will have the highest dipole moment value. Okay, but here the lowest electronegative atom is having the highest dipole moment values represented. So that is incorrect. So the correct options are B and C. Option C is the correct answer. Option C is the correct answer. Now moving on to one more question. In which of the following process the bond order increases and paramagnetic character changes to diamagnetic one? So let us calculate the bond order. So for O2, number of electrons are equal to 16, and for 16 the bond order is 2. And O2 2 minus, number of electrons is 18 and the bond order is 1. Here the bond order is decreasing, so it cannot be the answer. And for nitrogen, number of electrons is 14, so bond order 3. N2 plus means 14 minus 1, right? So it is 13. If it is 13, we have to subtract 0.5. So it is 2.5. So here also bond order decreases from 3 to 2.5. So it cannot be the answer. And come to NO. NO means nitrogen atomic number 7, oxygen atomic number 8. So 7 plus 8 is 15. The number of electrons is equal to 15. Bond order is 2.5. You use the trick table to find out the bond order, okay? And for NO plus 7 plus 8 minus 1. So what it is? It is 14. So 14 means it is 3. So the bond order is increasing from 2.5 to 3. Paramagnetic character also increases because in NO, which has 15 electron, it is paramagnetic. If it is 2.5, 15 means it is nitrogen. N2, if you NO plus, if you see, it is having 14 electron and all the electrons are paired in the bonding orbital. So the paramagnetic is changing to diamagnetic. And O2, if you see, O2 is 2 again, bond order. O2 plus is 16 minus 1, it is 15. 15 means bond order is 2.5. So the bond order is increasing, but for oxygen, oxygen is paramagnetic in nature. O2 plus is also paramagnetic in nature. In O2, we will have one unpaired electron. In O2 plus, sorry, here we will have two unpaired electron and here we will have one unpaired electron. Okay, so both are paramagnetic, but bond order increases. So the correct answer is option C, in which the bond order also increases and the paramagnetic character also changes to diamagnetic one. Got it? Now let's solve one more question. The bond order and magnetic property of acetylide ion are same as that of. So what is acetylide ion? Acetylide ion is C2 minus. So what is the bond order? For carbon it is 6, 6 plus 6 plus 2. So it is 14. Okay, it is 14. Now we have to find out the compound which has the same number of electrons. 14 means bond order is 3, right? And here O2 plus. O2 plus means 16 minus 1. So it is 15. So bond order will be 2.5. It cannot be the answer. And O2 minus means 16 plus 1. So it will be 17. 17 means it is 1.5. No. 1.5. N2 is 14 minus 1, 13. It is 2.5. No. NO plus is 7 plus 8 minus 1. So it will be 14. So if it is 14, the bond order is 3. So the correct answer is option D. NO plus is having the same bond order and the magnetic property is also same if the bond order is same. Okay. Most of the cases. Now let's solve one more question. The OO bond length in H2O. So let me draw the structure of H2O, H2O2. So this is taken as X. And the next F2O2. F2O2. This bond length is taken as, yeah, this is X in both the cases. OH bond length in H2O. This is taken as Y. So first of all, talking about X, H2O2 is having the highest X value. Bond length in X is longer. Yeah, H2O2 is having the longest OO bond length. But because here we are having fluorine, right? So what happens here? Fluorine will have lone pair of electron. Oxygen will also have lone pair. So lone pair repulsion occurs. So because of this, the bond length of FO will be greater. But here OO will be greater, longer than OO of O to F2. So it is longer, X is longer. So option B or D should be correct. And coming to the OH bond angle and OF bond angle, OH bond angle, if this is longer, obviously this is shorter, right? If one is longer, obviously other one will be shorter. So if X is longer, Y is shorter. So option B will be the correct answer. In H2O2, the OH bond length is shorter than O2F2. Got it? Now coming to one more question. According to MO theory, molecular orbital theory, the bond orders. We can easily calculate. I told you, you can calculate using trig table. O2. It is 16 plus 2. So it will be 18. If it is 18, the bond order is 1. Okay. And for CO, 6 plus 8. So 6 plus 8 is 14. Bond order is 3. And for NO, 7 plus 8 minus 1. So it is equal to 14. So again it is 3. So 1, 3 and 3. So option A. Okay. Coming to the next question. The bond dissociation energy is highest for. So we have fluorine, chlorine, bromine and iodine. So among these four, chlorine will have the highest bond dissociation energy because in fluorine, since the size of the fluorine atom is very small, inter-electronic repulsion will be very, very high. This inter-electronic lone pair repulsion. Repulsion is very high. Repulsion is very high, due to which the FF bond weakens. They weaken, and if the bond is weak, we can easily break the bond, right? So the bond dissociation energy will be low, but it is very high for chlorine. We cannot break this chlorine bond easily. Then comes fluorine, chlorine, fluorine, bromine, and iodine. Okay. So option A is the correct answer. Now, what is the number of unpaired electrons in the highest occupied molecular orbital of the species N2, N2 plus, O2, O2 plus? So in N2, N2 follows this order. Okay, N2. But O2 follows this order. This is bonding and this is anti-bonding. This is the anti-bonding. If energy is increasing like this, N2 will have 1, 2, 3, 4, 5, 6 electron. And O2 will have 1, 2, 3, 4, 5, 6, 7, and 8. So this is N2 and this is O2. So the number of unpaired electron in the highest occupied molecular orbital, that is highest occupied molecular orbital of the following species. So here we don't have electrons in highest occupied molecular orbital. So it is 0. For N2 it is 0. For N2 plus means I have to remove one electron from N2. So if I remove one electron from N2, I have to remove this electron. So if I remove, how many electrons I'm having? The highest occupied molecular orbital is having 1 electron. So N2 is having 1 electron. N2 plus is having 1 electron. Now O2, how many electron O2 has? Highest occupied, it is having 2 electron. O2 has 2 electron, and O2 plus means I have to remove 1 electron, right? So the last electron will go from this orbital. So here if you see, the highest occupied molecular orbital for O2 plus is having only 1 electron. So 0, 1, 2, 1. So option C is the correct answer for this question. Okay. Now consider the ions or molecules O2 plus, O2, O2 minus, and O2 minus. For increasing bond order, the correct option is increasing bond order. We can find the bond order easily using the trick. So first, let's start with O2 plus. O2 plus 16 minus 1. So it is equal to 15. If it is equal to 15, then it is 2.5. Right? Then for O2, we know it is 16. If it is 16, bond order is 2. O2 minus, it is 16 plus 1. So 17. 17 means it is 1.5. Right? And O2 minus 16 plus 2, which is equal to 18. So it is 1. So the bond order increases. O2 2 minus is having the least bond order, then O2 minus, then O2, then O2 plus. So it is given in option A. A is the correct increasing order of bond order. Okay. So very easy questions are asked from molecular orbital theory using bond order concept for both JEE and NEET. Okay, concentrate more on it. Now the correct order of bond orders of the given 3 ions, C2 2 minus. C2 means it is 6 plus 6. So 12 plus 2 is 14. If it is 14, bond order is 3. And for N2 2 minus, for N2 it is 14. 2 minus gain 2 electrons will become 16. So it will be 2. And for O2 2 minus, O2 16, 16 has gained 2 electrons, so it is 18. It is 18, it is 1. So O2 2 minus, then N2 2 minus, then C2 2 minus. So the correct answer is option B. Correct answer is option B. Okay. Now, The correct order of energies of molecular orbitals of nitrogen molecule is, so we have seen the diagram, right? So on the bottom we have sigma 1s, then sigma star 1s, okay, then sigma 2s, then sigma star 2s is higher in energy than sigma 2s. Then above this we have two orbital. One is pi 2px and the other one is pi 2py. They both are having the similar energy. Then above this we will have sigma 2pz. Then after this we will have pi star 2px, which will be equal in energy with pi star 2py. Then these two, above these two we will have sigma star 2pz. Okay. So this is the correct order of increasing order of energies of molecular orbitals of N2. So where it is given in option D. It is given in option D. Okay, very easy. And which among the following is incorrect statement? So let's go from the first. We have to find out the incorrect statement. The bond orders of the four species are given. O2 plus. O2 plus is 2.5. O2 plus means how much? 16 minus 1, right? So 16 minus 1 is 15. If it is 15, it is 2.5. Yeah, it is correct. And for O2, it is 16. So the bond order will be 2. That is also correct. And for O2 minus, it is 16 plus 1. So 17. If it is 17, it is 1.5. That is also correct. And for O2 2 minus, it is 16 plus 2. So it will be 18. If it is 18, bond order is 1. So all the bond orders are correct. So the statement is correct. C2 molecule has 4 electrons in its 2 degenerate molecular orbital. That is also correct. Because if I want to draw the 2p orbital for C2, so energy is increasing like this. So this is the 2p orbital, 3 2p orbital of 2 carbon. Okay, it will have 2p2 configuration, 1s2, 2s2, 2p2 for carbon, right? So this is the atomic orbital. We have 4 electrons. So 1, 2, 3 and 4. So this is how we have to fill the electrons in the molecular orbitals. And C2 molecule has 4 electrons in its 2 degenerate pi molecular orbital. So this is pi 2px and the name of this orbital is pi 2py. So those are the pi orbital and they are degenerate. Degenerate means same energy. Okay. So they are same energy orbital which has 4 electrons. So option B is also correct. Then coming to option C, H2 plus ion has 1 electron. So what is the MO diagram? So these are the hydrogen. A hydrogen have 1s1 configuration. If I want to draw the MO diagram for hydrogen, I will fill up these 2 electrons here. This is for hydrogen. If I want to draw for hydrogen plus, what I have to do? I have to remove 1 electron, right? Just remove 1 electron. So the statement says hydrogen H2 plus ion has 1 electron. So that is also correct. O2 plus ion is diamagnetic. No. In O2 plus, if you see for the 2p configuration, we will have bonding and anti-bonding. So in bonding, all the electrons are filled. When you go for anti-bonding, for O2, we will have 2 electrons. And O2 plus means you have to remove 1 electron. So that electron will go from here. So O2 minus ion is still having 1 unpaired electron, which is paramagnetic in nature with 1 unpaired electron. But here it is given as diamagnetic. So option D is incorrect. Option D is incorrect. Okay. Then moving on to one more question. The correct sequence of bond enthalpy of carbon halogen bond is. You can see 4 compounds are given. CH3F, CH3Cl, CH3Br, CH3I. Okay. So on moving down the group, the carbon halogen bond length increases. Bond length and bond enthalpy, they are inversely proportional, right? So if one increases, the other one will, the bond energy will decrease. Okay. So CH3, I will have the least value, then CH3Br, then CH3Cl. The one which is having the highest bond energy is CH3F because bond length is very short. So it is very strong. Energy required to break the carbon-fluorine bond is very, very high. So this particular order is given option C. Okay. Fluorine, chlorine, bromine, and then iodine. Now, coming to the last question for the session, identify a molecule which does not exist. Which does not exist. So helium and beryllium. So these two molecules does not exist. Okay. Others will exist because in these two molecules, the bond order will be equal to 0. Suppose if I want to draw for helium, so helium will have 1s orbital with the 2 electron. So I'll take 2 helium with 1s2 configuration. Now I have to fill those electrons in bonding and anti-bonding, sigma 1s and the sigma star 1s. So 4 electrons are there. 1, 2, 3, 4. Now if you want to calculate the bond order, in Nb minus Na divided by 2, number of electrons in bonding is 2, anti-bonding is also 2 divided by 2. So it is equal to 0, right? So 1s, 1s. So since the bond order is very, very less and bond order is directly proportional to stability, bond order is 0. So the molecule stability is also 0. It is unstable. Helium molecule doesn't exist. Okay. Whereas oxygen, carbon and lithium, you can see for oxygen, bond order is 2 and for carbon, it is 12, right? So the bond order is, it is actually 6 plus 6, 12, then 1, 2.2, 2.0. It will be 2.0, bond order is 2.0 again, 2 again, like oxygen. And for lithium, the bond order will be 1. So here the bond order is 0. So helium molecule doesn't exist. Okay. Fine. So this is all for today. So we have completed the chemical bonding chapter here. As yesterday we have seen part 1 and today is part 2. And in the next session, we will meet up with one more new lesson for you. So till then, thank you so much for listening the lecture. Take care. Bye-bye.